Today we're going to be reviewing a little bit about titrations. This is a general laboratory experiment. In the scope of this course, we're going to focus on acid-base titration, although there are other titrations that are able to be used typically in the laboratory. In AP Chem, we're talking about acid-base titration. I would probably introduce this experiment in regular chem during most years, which is why I'm reviewing it now. But this is something that we will be going into more detail later in the year. So if you're not very familiar with titrations or don't feel like you know everything at the end of this video, that is completely fine. Do not worry. So this is the general setup of a titration. The most important instrument in the titration is the burette, which is this glass tube here. You read a burette a little bit differently than you would read a graduated cylinder or other instrument in the lab, and we'll be going into more detail on how to read the burette. The burette is important because it tells us the volume of titrant that we are adding to an unknown solution. So the titrant is a chemical where A, we know the volume, and B, we know the concentration of this titrant. This is a stopcock, which is a little addition on the end of the burette. It's basically, you can turn it to let a steady stream of chemical flow. You can turn it so that it's only adding a drop of chemical at a time, which is typically what we use during the titration. Or you could turn it so that no titrant flows at all. So we use this to control how much titrant we are adding to the analyte, which is a second chemical solution that we do not know the concentration of. We know what volume we start with, but we don't know the concentration or molarity of that chemical that we're starting with. With the analyte, we also add an indicator. In acid-base titrations, a lot of time this is phenolphthalein, which again is clear with an acidic solution, and then it turns pink as the solution becomes more basic. With acid-base titrations, we are focusing on a neutralization reaction occurring. With a neutralization reaction, we're adding acid and base together to create water and a salt. Typically that salt is soluble, so it doesn't exist as a solid. It exists as ions in an aqueous solution. We talked in the previous video about different theories that define acid and bases. For titrations, typically we're using Arrhenius acid and bases. So all acids will have H+ ions in a solution, and all bases will have OH- or hydroxide ions in a solution. When the neutralization reaction is complete, that means that the number of hydrogen ions is equal to the number of hydroxide ions in the solution. So these are chemical equations. Typically you know what your acid and base are, so it's not like you have an unknown acid or base. You know the chemical formula of them, you just don't know the concentration. So here is an example where we have hydrochloric acid and sodium hydroxide in a titration. With this setup, I'm going to go back to this slide for a second. Typically we have the acid here and the base as the titrant, but you can do it so that your base is your analyte and your acid is the titrant. But typically, we have the acid as the analyte in most setups, but you can switch it up. That's not too important. So here, we are titrating HCl, hydrochloric acid, with the base NaOH. Based on this chemical equation, remember that for neutralization to occur completely, it's a 1-to-1 ratio between H+ and OH- ions. So based on the coefficients of this reaction, we know that only 1 mole of sodium hydroxide is needed to neutralize 1 mole of HCl, because both of these have a coefficient of 1, and there's only 1 OH and 1 H in these two chemical formulas. So it's a 1-to-1 ratio. You only need 1 mole of NaOH to neutralize 1 mole of HCl. But if you look at this equation, in this reaction, we have HCl again, hydrochloric acid, but this time we have barium hydroxide. With barium hydroxide, the chemical formula is BaOH2. Okay, so to balance this chemical equation overall, hydrochloric acid has a molar coefficient of 2. So this is saying that 2 moles of HCl react with every 1 mole of barium hydroxide. That means that we have twice as much HCl as we do barium hydroxide when the neutralization reaction is complete. Another way of thinking about it is that you only need half a mole of barium hydroxide to neutralize 1 mole of HCl. Okay, so I'm talking in terms of neutralizing HCl because, again, in most titration reactions, your acid is your analyte and your base is the titrant. So we would only need half as much barium hydroxide to neutralize 1 mole of HCl. The reason we know that is because of the coefficients of this chemical equation. Oh my goodness. The equivalence point is a point in the neutralization reaction where the neutralization reaction is essentially complete. Or in other words, there are equal number of moles of hydrogen ions and hydroxide ions. We use titration to determine the unknown concentration of an acid or base. Again, typically this is of the acid, the analyte. The solution with known concentration and volume, otherwise known as the titrant, is added to a volume of solution of unknown concentration. Again, typically it's an acid, but doesn't always have to be. Again, acid-base titrations are not the only type of titration, but are definitely the most common in the chemistry lab setting. With indicators, we talked a little bit about different indicators in the previous slideshow, but an indicator basically has a color change that tells you when the pH has changed. With titrations, a lot of times we use phenolphthalein because it's clear with acids and pink with bases. Now, it doesn't turn like bright fuchsia pink as soon as it's basic. It's just going to be a slight pink hue at first, which is why you have to watch your reaction occurring very, very carefully so that you know immediately when the reaction has reached the end point. With titration reactions, we basically say that the end point is equal to the equivalence point, even though they're not 100% the same. So at the equivalence point, when number of H plus and OH minus ions are the same, your solution is still going to be clear because the solution isn't basic, it has a pH of 7, which is neutral, typically. We'll go into that a little bit later too. But then when you have slightly more base and you have a slight hue change due to your indicator, that is when the end point occurs. So when you stop adding the titrant typically. So there are 4 basic steps of a titration experiment. First, you have a measured volume of acid of unknown concentration, and you put it in a Erlenmeyer flask. I think I called it a volumetric flask at the beginning, sorry, but an Erlenmeyer flask. Then you add several drops of an indicator and mix it by swirling. You can also use a stirring rod, which we will go through with laboratory setup at the beginning of the year. A burette is filled with the base of known molarity, and you would also write down the initial starting volume of base. Then you open the stopcock and add it slowly to the acid while the flask is constantly swirled to ensure mixing. Again, you can use a stirring rod manually, or you can get a magnetic stirring rod that can be used. The stopcock is closed at the exact point at which the indicator just changes color. So again, with phenolphthalein, it's not immediately a bright pink. It's going to be like a clear, transparent pink, which you would stop adding the base. You can also plot a titration curves. With titration curves, typically you go beyond the equivalence point. So you are making a graph with the pH of a solution versus the volume of titrant added. If the titration is a strong acid and strong base, the pH at the equivalence point is equal to 7. So strong acid, strong bases is typically what we would use where we have the indicator slightly changing to the point of the basic solution. But if we have a weak acid or weak base in any point, the equivalence point, the pH is not going to necessarily be equal to 7, which is why we would definitely use a titration curve to determine the equivalence point of the reaction. So in a weak acid-base titration, pH is greater than 7, and with a strong acid-weak-base titration, the pH is less than 7 at the equivalence point. This has to do with conjugate acids and conjugate bases of weak bases and acids. We'll go into more detail with that later on. Right now, I just want you to be aware of these 2 bullet points here. We'll go into explanation of why later in the year, so don't worry about that yet. So this is, again, what a titration curve looks like. You have pH of the overall solution that is in the Erlenmeyer flask versus the volume of base or acid, the titrant, that is added. So the equivalence point with the titration curve is going to be the point at which the slope equals 0. So at that point, it's right here. It's a straight up and down line. At this point, it's right here. Since both of these are strong acid, strong base titrations, the pH is 7 at the equivalence point. So when you're reading this, here we are starting with an acid in the Erlenmeyer flask. So we have a low pH. As we add the base, the pH slowly increases until the equivalence point is at 7. At this point, we go beyond the equivalence point. So we keep adding base. pH continues to rise until it's closer to the pH of the base that is added. I'm having trouble with words today. Here we have the base as the analyte and the acid as the titrant. So we're starting with a high pH, slowly adding acid until the equivalence point where pH equals 7. Then we continue adding acid and the pH continues to decrease till it's closer to the pH of the strong acid. Here is what where we have a weak acid versus a strong base. You can see that the pH is slightly higher than 7 at the equivalence point. So here, our indicator would start to change color before the equivalence point. So that's why titration curves are helpful for anything where your analyte or your titrant is a weak acid or weak base. You want to use a titration curve versus just using an acid-base indicator, because your color change is going to occur slightly before the equivalence point. So again, we have a weak acid, so you can tell that the starting pH is slightly higher than the strong acid. And then we're adding a strong base, so the pH is rising. Here is where the pH is equal to 7. Slope is not 0 yet. So here at the equivalence point is where the slope is equal to 0, pH higher than 7. And we continue beyond the equivalence point, again, just to get this nice graph so that we can actually find the point where the slope is equal to 0. So we can do calculations with titrations. Remember that at the end point or equivalence point, the moles of acid equal the mole of base, specifically H plus and OH minus. To find number of moles, you can take the molarity times the volume, because molarity is moles per liter, multiplied by liter volume would give you number of moles. So since the number of moles of acid is equal to the number of moles of base, we can use this equation. Molarity times volume equals molarity times volume. A stands for acid, B stands for base. So here we have an example problem. We have a titration performed. We add 20.7 milliliters of 0.5 molar NaOH, and that is what is required to reach the endpoint when titrated against 15 mils of starting volume of HCl of unknown concentration. We want to find the molarity of the acid, or the concentration of the acid. So we're going to start with our general setup. Ma times Va equals Mb times Vb. And we are solving for Ma, so I'm going to rearrange that equation just a hair, divide everything by the volume of the acid. Everything on this right side of the equation is known and is given in the problem. So we can basically plug and chug. Now with volume, in the previous slide, I said liters. But since both of these volumes are in milliliters, if we were to convert to milliliters for both of these, that conversion basically cancels out in this overall reaction. So as long as my unit is the same for volume, I can keep it in milliliters just fine. If you would like to convert to liters, you definitely can. Nothing is stopping you. So here I'm going to plug in the molarity of my base, 0.5 molar, times the volume of my base, 20.7 milliliters, and divide by my volume of acid. When I do that, I will wait till that little bar disappears, but you get 0.690 for your molarity or concentration of your acid. Okay, so that is it for our titration review. Please let me know if you have any questions.